Welcome to my set, Jackson. So I was originally going to get a brain transplant, but then I changed my mind. There's bad fun.
I don't want to present.
I hope everybody seen many of you guys
go home.
were at Converge B-Sides, so if you were, awesome. Good to see you here again. Hope you guys had fun. If there's any comments, concerns, things you liked, things you didn't like, let me know. We'll pass them on to our crew. Otherwise, I don't have a lot going on. Anybody else have announcements?
I have an announcement.
Oh, yeah.
Yes, I do. So, I'm inviting everyone out to my house on Saturday from 2 to whenever. I live on a lake. I've got a couple kayaks, a paddle boat, and whatnot. We can go swimming and have a fire. And
Sweet.
I've got a bunch of beer left over from my son's graduation party I need help getting rid of. So if you want my address, let me know, and I can give you a card, and away we go.
Awesome.
Luke has one too.
Luke? Oh yeah, I just accepted a position to work here at Consumers, so.
Sweet.
Now watch all your stuff.
Hey, there's Sam.
Any other
Better late than never, I guess.
cool things? All right, then I'll hand it over to Chris.
Okay. So you got the stream live and everything, Kyle?
What are you talking about?
We're good?
It's recording and it should be
Well,
streaming.
if it's recording, we're good to go then.
Yeah.
Fine.
Double down.
Did you tweet out the link?
That's right. I'm working on that. Jeez, it's not gonna start.
Oh, you're a
until
mess
I'm
tonight.
watching it. I am a mess. Well, it started because my stupid video.
I forgot to mention, bring a bathing suit and a camp chair. You got something to sit on.
All right. Now that Kyle's sorted out his laptop, let's get started. So this is going to be an intro into writing Windows 32-bit shellcode. So obviously you guys know who I am, but this is a slide deck that I'm potentially preparing for some conferences. So I will still mention this though, that I've thrown my Keybase link up there because a couple of the scripts we're going to talk about, as well as the shellcode that I've written, can be found on my GitHub, as well as about the second half of this presentation is written up as a blog post on my website. So rather than trying to give you guys a bunch of links that you'd have to go try to take a picture of or ask me about later, if you just go to the Keybase link, my website, my GitHub, my Twitter, everything is all linked off of there. So you can find it much more easily than me giving you a bunch of other links. So our agenda today is to work through this very heavily Overwatch themed slide deck to talk about what shellcode is. We're going to do a quick review of the stack and CPU registers and some basic instructions for anyone that might not be familiar with that, just so you can hang in there as we work through how we can start writing some shellcode. And then we're actually going to talk about how you can debug shellcode using Python and actually get into writing some shellcode and demoing it and show you how that stuff works. So first off, we have to talk about what shellcode is. If you've ever worked with any kind of exploit or used MS Venom or really Metasploit, you've probably worked with some shellcode. But the term shellcode gets a little bit hazy. It's actually pretty limiting. Shellcode is basically just assembly language. It's no different than any other code. Shellcode isn't its own special type of programming language or anything like that. We just call it shellcode because typically it's code that gets us a shell. It's a very simplistic term. But it can do more than that. We can have it run commands. We can have it make changes to the computer. We can have it do really anything we can come up with. It doesn't have to just get us a shell. But we do, we're going to call it shellcode. The core thing that makes shellcode, in my opinion, is its instructions we're injecting into a running process. So usually, if it's shellcode and we're trying to get a shell, it's because we've run some sort of exploit. We've, a buffer overflow, for example, and now we're running inside of a process. And those instructions have been crafted in such a way to run within that process. And we'll talk a little bit more on that later, but that's a very important distinction when you're talking about shellcode, because sometimes you have shellcode that is meant to run inside of a process and will not run outside of that process because the environment isn't right. And like I said, I'll touch on that a bit more later, but just something to keep in mind as we work through this. So a few basic characteristics of shellcode. For one, as many of you probably know, we usually refer to shellcode as in how large it is in bytes. It's like the shellcode is 252 bytes. It's just how we count it. It comes down to like how big the opcodes are in that shellcode. And what those are is, if you look over there on the right, we start off with assembly language. If we're writing our own shellcode, the human written shellcode is assembly language. So we start off with, say, XOR EAX against EAX in assembly. When that gets compiled, that becomes 33C0. It becomes the machine code, the hexadecimal version of those instructions. Then we have to format it for our scripts, for our exploits, and usually that requires doing a little /x formatting. And then it's ready to go. And each one of those, the hexadecimal notation there, each one of those is 1 byte. So XOR EAX against EAX would be a 2-byte instruction. So when we're saying like this shellcode or these commands are X bytes, we're referring to basically how many hexadecimal characters are in the shellcode. It's like a basic way to look at it. Opcodes can actually be 1 to 3 bytes, but that's getting into territory we don't have to get into for the basics. Today we're going to be working strictly with the Intel x86 architecture. The instructions you use for your shellcode and how shellcode works varies by architecture. So if we started talking about ARM, that would be a totally different thing. Many of the basics still apply, but it is different. There are different instructions. One of the major things is that x86 actually has specific instructions for dealing with the stack, which we'll talk about in a minute, which makes it a little bit different and allows us to do certain things that are very handy. Yeah, pretty much everything else we have covered there on the slide. So I can't really think of anything else that you guys would have to know about shellcode to begin. So really, let's start talking about how we might test some shellcode once we've written it, just so we can cover this before we get started. The way that I like to do it is using Python and CTYPES. CTYPES is a library, comes with Python. You just import it, and it'll let you execute shellcode under the Python process. And then you can do things like importing DLLs and setting up the environment for that shellcode to run. So this is an important distinction there, that importing DLLs and setting up the environment. So like I mentioned, you can have shellcode that won't necessarily run on its own because it's assuming that a certain Windows library has already been loaded into memory. You know, for example, if you were executing a buffer overflow against an FTP server, you have a process that is therefore like using networking. It's probably using the WinSock API. It's already loaded the Windows Socket API library. So we can just assume that's already in memory and start referring to it and understand that it's going to be there. But if we just say start using Python and we load up something that's going to use the WinSock DLL, Python doesn't load that by default. So we're going to have to load it manually with CTYPES before we can test out that shellcode and debug it. So this is just a little bit of a test code sample. I have this on my GitHub. This is the skeleton script I use for testing shellcode. We'll take a look at it a little bit later. But this is how you can start getting using CTYPES. You import CTYPES, you provide your shellcode as a byte array, and then I have a couple of debugging tips that I like to use. First is this: I usually leave it commented out, but a breakpoint that I put at the start of my shellcode. And then I have this guy down here, just an input I just have it show up debug pause or whatever you want to show it. Because the thing about running shellcode with Python and CTYPES is that once you run that script, the shellcode runs. You're not going to have a chance to attach a debugger to python.exe before it runs. So a nice way to do this is first you run your script, it hits that pause before the shellcode ever executes, which is the other side of the screen. And you have to hit enter before it'll continue with the script. At that point, you can attach a debugger to python.exe and then hit enter and off it goes. And then that breakpoint's there so that as soon as it starts to execute the shellcode, the first thing it does is break. And then your debugger will say, hey, we've hit a breakpoint, what do you want to do? And then there's your shellcode right there in your debugger, and you can step through it line by line, see what it looks like, in the debugger in memory, and work from there. Then over on this side, these are the different sections where shellcode is referenced. So what I like to do is, if I'm going to mess around with different versions of my shellcode, I just call it shellcode, or whatever you want to call the variable. I leave it the same, and then I'll just rename the variables, or move one as the last one that's been declared to kind of move things around without having to change every instance of that variable each time. Just a couple of tips for if you want to go and start playing with this and have a bunch of different shellcode samples. So let's do a review of memory and CPU registers, because we're going to be doing a lot of this with our shellcode. So first off, we have the stack. Stack, if you're unfamiliar with it, it's a reversed region of memory where your process that you're going to be working with, whether it be the Python process or a process you're injecting your shellcode into, where it's storing its data. The stack, the important thing to understand is that the stack is FILO. Some people call it LIFO. FILO is first in, last out. LIFO is just last in, first out, just another way to say it. But the point is that the stack works like you're stacking books. It builds upwards. So the first thing you put on your stack is going to be at the bottom of the stack. And if you want to get at that thing at the bottom of the stack, you have to remove everything off that what you put on top of it. So if you, as we're pushing things to the stack, where this comes into play with shellcode is we're often pushing things backwards. So if we're pushing parameters like 1, 2, 3, 4, we push 4, 3, 2, 1. So when it gets popped off of the stack, they're in the right order for our functions. x86, as I mentioned earlier, has specific calls for interacting with the stack. Not necessarily true for other architectures. But in this case, we're going to be doing a lot of pushing, and push is just a very basic instruction that pushes something onto the stack. It goes to the top of the stack, and then we can work with it from there, push more things on top of it. Pop removes the top thing of the stack off of the stack. We're not going to be doing a whole lot of popping in our example shellcode here today, but pop does come up a lot if you are, say, trying to backdoor an executable, or you want to, the process you're exploiting, if you want to then be able to continue running after the shellcode runs. You're often like pushing and popping register values to try to preserve them so you can put them back where they were before your shellcode ran to let the code flow continue normally. But we're not going to be doing much with pop today. Endianness is another thing we have to pay attention to. This is a real thing. It's a kind of a funny word. It's a little bit hard to say. It just sounds like you're saying Indian. But basically this is just the sequential order in which bytes are represented in memory. So there's big and little endian. With Intel x86 and Windows, we're going to be using little endian. And little just means that the least significant byte is put into memory first. So that means essentially that our addresses and things like that we're putting into memory are going to be flip-flopped. They're going to be reversed. This can get a little bit confusing. So just like with this example here, let's say we want to push the ASCII string boop to the stack. So with what I just told you, it would make sense that if boop was 70, 64, 64, 42, or 64, 6F in hex, that we would push it as like that second one, we push it backwards. That is true, but except since this is assembly with that push, it's actually the first one is the correct one. However, if then we were going into the compiled assembly to make changes to it, that's when it shows up as 42, 6F, 6F, 70. And that 68 there is the hexadecimal representation for the push instruction. So I don't want to, it gets a little bit confusing. Basically, if you have shellcode that's totally bombing and you can't figure out why, maybe go and check your endianness because it might be that an address is not in correctly and it's referencing a section of memory that just doesn't exist. Speaking of referencing memory, we're not going to have to worry about this today. My examples are all going to be actually Windows XP, Service Pack 3. But just to be aware that if you're talking about exploit development and taking your shellcode in that direction, referencing certain sections of memory can become problematic. In Windows Vista and beyond, you have ASLR to worry about, which is address space layout randomization, which basically just means that the addresses of Windows functions are going to change between reboots. And then there's also data execution protection, which is in Windows XP and beyond, which can set certain sections of memory in a process as non-executable. So this is often used as buffer overflow protection. So if they know there's a potential for buffer overflow at a certain area, they want to make sure that where you're going to overflow into would be non-executable and your shellcode wouldn't run. We don't have to worry about that today because we're just going to be running it with Python to give you the basics. But just keep that in mind if you start moving into like exploit development. But what we are going to have to grapple with today is the idea of Windows addresses changing between service packs and versions. So Windows has a unique ability to frustrate shellcode in that between updates, it's often changing the address of its functions. They're not consistent. So that becomes a problem if we hard code an address into our shellcode for a certain function. Then it won't work on any other version of Windows except for that one specific version, like Windows XP Service Pack 3. It won't work on Service Pack 2. It won't work on Windows Vista. It's just something to keep in mind. The CPU registers, there are quite a few of them. They do have common uses. You can go and look up Intel's recommended uses, the conventions they've set aside to say like this register is meant for this and this. When it comes to shellcode, we can kind of use the registers however we want. Just the thing to keep in mind is that these registers do have a purpose in some cases. Like for example, ESP. The ESP is the stack pointer. This is always going to point to the top of the stack. This is important to remember because we're going to use it a lot for making pointers to things. Also, EAX is the accumulator register. It's often used as like a calculator. It can be used for a number of different things, but it's good to keep in mind this often holds return values for functions. So some of the registers, as you're working with shellcode, you'll learn what they do and kind of their typical uses. And that's important to know just because you don't want to step on your own toes. So for example, if we call a function, like we will later, that gives us a return value that we need to preserve and use later, and then we're using EAX to calculate a value, we throw away that return value, and then we've stepped on our own toes, and our shellcode's going to break because we're not going to have the value that we need. Same thing if you were trying to, like I mentioned earlier, backdooring an executable, or you're injecting into a process. If you want that process to continue to be able to function properly after your shellcode runs, it's probably already using those registers. So you're going to want to preserve the values in there, understand what registers it might not be using that then you can use for your shellcode. So let's actually talk about the real purpose of this presentation and talk about actually making some shellcode. Let's keep it loud. So first we have the easy way. The easy way is like using MSF Venom. It'll generate the shellcode for you. It's reliable. It's great. Why would you ever not just use MSF Venom to create your shellcode? The hard way would be like just using your brain to output some assembly. Maybe adding in some coffee for some motivation. But obviously a bit more difficult and far less convenient than using MSF Venom. However, there are some reasons you would want to do it the manual way. Now, one thing that MSF Venom does for us very conveniently is, if you've used it before, you're used to giving it like lport equals, lhost equals. It'll automatically give you shellcode that references like your IP address and port for the payload you wanted, and that's because it's constantly pulling from a library of assembly files that it has. You can go see them on the Metasploit GitHub if you're curious. There's a whole bunch of assembly files that are in pieces. You can go through. It can be kind of a maze to figure out where it's pulling from here and here and here to create this one payload. But you can eventually get an idea of what assembly is being pulled in to create these payloads. And that's static. That stuff doesn't change. So it's reliable in that way. But it also means that the payload size will be consistent. And one of the methods that it does in order to remain dynamic and work across platforms, because if you've used it before, you know that, like what I said earlier, that addresses change, and therefore your shellcode will only work on a certain version of Windows when we're talking about Windows, and we are here in this presentation. But what MSFM does is it uses certain techniques that dynamically look up the addresses at runtime. However, while that's convenient, when looking up those addresses takes a lot more instructions. Like if you look at shellcode that includes dynamically looking up the Windows addresses, if you're calling multiple functions in the shellcode, like you would for a reverse shell, for example, there's many more bytes per function call that have to be run, or you have to be included in the shellcode in order for it to find those functions. So shellcode begins to inflate in size very quickly when it's doing that, which we kind of have to do if we want the shellcode to be flexible. But at the same time, if we have, say, an exploit, as like a pen tester, if you're trying to work with an exploit that has a very small buffer or you don't have much space to work with, then you might be kind of screwed if you're just relying on MSF Venom. And that's when it can be handy to say, look, I'm really just interested in exploiting this Windows 7 box. I have an exploit that's working on it. I just need shellcode that I can put into this exploit as a payload. And if you can write your own shellcode, you can make it much smaller by hard-coding the addresses or using alternate functions and alternate instructions that can sometimes be smaller than what MSF Venom is relying on. And so there is a trade-off. It's going to be more work, and it's only going to work on like that one target, but it can be have a big payoff if it's your only option. So let's take a look at some comparisons and see if we can how our shellcode stacks up to MSF Venom. So let's look at a very simple payload first with MSF Venom. We're going to generate just the message box payload, the Windows message box payload, and we're going to have it say Sombra says in the title and boop in the text box. It comes out, it's 262 bytes, which is actually kind of big for what it's doing, because it's just going to call one function, right? So it seems kind of large. So we're going to see if we can try to do better. So the first thing we have to do when we're writing shellcode is we need to go to the Windows Dev Center and, formerly called Tech Center, sometimes called MSDN, and we need to look up the, and this is kind of important because you can find like .NET versions of the documentation. You want the version for C, and find the function, and we need to take a look at it and look at all the parameters and figure them out, because sometimes they can be a little bit tricky. They don't look quite like they seem. So in this example, the function up there at the top is kind of an abstract, because it's not actually wanting the ASCII strings boop and Sombra says. It wants the pointers to those strings. So knowing that, and then looking at that it wants just a couple of integers for the other two values, kind of sandwiching the ASCII strings in between, we know we're going to have to provide a 0, a pointer, another pointer, and a 0. So we can start writing that shellcode. And if we're going to target Windows XP Service Pack 3, we can manually hard code in that address, and our final shellcode actually comes out to 39 bytes, a far cry from 262 bytes. So this is just the best way I can think of to highlight that difference, where what MSF Venom doing, dynamically looking up those addresses, and it also does a couple of other things we'll take a look at in a second. The shellcode gets massively inflated, which is often fine, but in cases where maybe you need a very, very small piece of shellcode to fit into an exploit, that's when manually writing your own shellcode can be hugely beneficial. So let's just step through this real quick. I don't want to spend a bunch of time and bore you all walking through shellcode, but there is a couple things I want to highlight that are important to keep in the back of your mind if you start writing your own shellcode. The first is looking at just this first instruction here, that 33C0, the 0, this is XOR EAX against EAX that we kind of looked at earlier. So this is just a neat trick for shellcode where we don't want to put a 0 into our shellcode. We don't want to put a null byte in, the double 0. The reason, we actually could here, because we're just going to run this with Python. Python won't care. But it is important if we're injecting this into a process, because a null byte is a string terminator, which means that will just kill our shellcode if we're injecting it into a running process. So just as practice here, we're going to try to avoid putting zeros into our shellcode, and we're going to use an XOR function to make that register equal 0. Because if you XOR something against itself, no matter what the value in EAX is in at the time, if you're XORing against itself, you're always going to get 0. So it's just a nice trick. And there's other options to that too. You can kind of combine two binary, use AND instructions to add two binary numbers together to make them equal 0, and some other tricks similar to that to set something to a value that you want that might be a bad character for your shellcode. And then just highlighting here a couple of things. One, you can see that we're pushing the string backwards, it looks like. Like we talked earlier, the stack is first in, last out. So we're going to push the last part of the string first, and then the middle part, then the first part, so that when it's popping off the stack, it'll be in the right order. Now, it's chunked up this way in 4 characters apiece because our ASCII strings need to be pushed to the stack as D-word values, which just means 4 characters apiece. So we need to split the strings up into groups of 4. Now, in this case, it just so happens that Sombra says is evenly divisible by 4. But let's say that we weren't including that semicolon, or it was just like 1 character short for some other reason. We can actually just pad it. So often it's not a complicated problem to solve. Like Windows doesn't care if there's extra spaces in the command. So we could have just added a space to the end of it to pad it out. You could add a no operation command or something else there that was just wouldn't, as long as it's not going to break the command that you're running, it doesn't really matter. Windows won't care. But just it does have to be pushed as 4 characters apiece. And then again, just highlighting that we're also pushing the parameters for message box backwards. So we're pushing 0, the caption, then the text, then that first parameter. Again, just pushing it all backwards. I also, you saw it there in the previous slide, but just to be fair in our comparison of the bytes, one thing that MSF Venom does, especially if you've ever messed around with Metasploit and you've seen like that exit func setting for the exploits, which that's the exit function. So if we were just to run the shellcode with just the message box, like Python would crash, or whatever program was running would crash, because once the message box was closed, Windows sees that as a process just died for no good reason, so it thinks it encountered an error. So we can call the one of the exit functions that Windows has. In this case, we'll call exit process to tell Windows, hey, kill this process. It's fine. We're not, everything's exiting okay. So we'll call exit process with a 0 code, and that adds a few bytes. But we can hard code in the address from kernel32.dll for exit process, and it just bumps us up to 47 bytes. Still a far cry from the 262. And either way, the results are the same. We get that same message box. The difference is the size. And we can try different instructions, move, do some different things, but that difference is, the big one is the size. But also important to understand is that our shellcode that we just wrote, up here, only works on Windows XP Service Pack 3. It won't work anywhere else. We would have to update the addresses, then it would work. We could just update the addresses with the right addresses for Windows 7 Service Pack 1 and be fine. But until we do that, it wouldn't work. So let's show you guys just a quick demo of what this looks like.
Windows XP.
Yes, Windows XP. So here's an example of the, if you guys can see that okay, I can try to make it a little bit bigger. Is that okay? Yeah, good enough. So this is just what the test script looks like. This is what we looked at earlier, but I've added a bunch of shellcode to it. But it's the same script. Up here, you can see that I'm loading a DLL that we're going to use for a later demo. And then here's a bunch of shellcode that I've had in here for testing around and screwing around with. But then here is our message box shellcode. So I'm just going to name this as shellcode. And we can just run this with Python. There we go. So there's that debug pause. And whoop, it works. All right. Oh no. There we go.
I have a question.
Sure.
Once your push command start the x68, which is the push command, right?
Mm-hmm.
But then there's several others. You're pushing 0 and it's x50.
Oh yeah. So x50 is push EAX.
Okay.
So when you're the hexadecimal notation for push when you're like pushing a value is 68. And that means, push this, this D word value that follows it, like push this address, push this string, whatever it might be. And then X50 is push EAX, and there's like a 51 and a 52 for the each register has its own like dedicated opcode for saying push this register to the stack.
Okay.
All right, so let's look at something a little bit more interesting and talk about building a connect-back stager. So if you've probably used a stager before, if you ever messed around with like Meterpreter, or many other Metasploit payloads. But the way a stager works is, for one, we have that initial exploit, or someone they click on an executable, we sent them in an email, whatever it might be, and they initiate the first, the stage 1 shellcode, which is our stager. And then what that does, the only thing it does is it says, cool, I'm going to connect back to this IP address and port that I've been given, and I'm going to expect to receive more shellcode. So it gets executed, and the victim connects back. The listener that we have set up on the attacking machine responds and sends back the stage 2 shellcode, which is probably shellcode that was much too large to fit into that initial exploit, or it was just too big. You didn't want to worry about trying to transmit it over the network, so you waited for that connection to be established and for it to be able to fed back in via the stager. The way that works on the Windows side is just going to make heavy use of the Windows Socket API, and there's a few steps that have to take place, and each one has to work in this order for it to work. The first thing is we have to actually initiate the WinSock API, and each process has to initiate the API itself. So just because, say, like an FTP server is running on that machine doesn't mean that the WinSock API has been initiated. It's been initiated for that FTP service, most definitely, but each process has to initiate it on its own. So that has to be done first if it hasn't already been done by, say, the process that maybe we're exploiting that FTP server, so we're good to go and we can skip that. Then we have to call the socket function to make a new socket. Then we call connect, which is just the process that says, hey, connect to this IP address on this port. Do it over TCP, gives it all the specification for how it's going to connect. And then we have receive, which is the final, last important piece, because the socket, if we start sending data back, if the socket hasn't already called receive for that socket, then it's not going to know what to do with it, and connect will have already disconnected. So receive tells it, now wait for data to be sent back, here's the size buffer we need, and then let's execute it. And then, like I was mentioning earlier, and kind of just mentioned now, sometimes depending on the situation, we can skip steps if we know, for example, this FTP server I keep referencing, if that FTP server is what we're exploiting, well, we can say, hey, look, it's already going to have initiated the WinSock API, so we're just going to skip that step. Our stagers didn't have to try to initiate it again. And you can keep going depending on how you want to tailor your shellcode. Maybe you have a way to get a hold of the socket descriptor that got called from socket, and you could skip socket then and just call connect and receive, which is just another benefit of being able to, if you're writing your own shellcode for a specific target, you can take those kind of variables into account. So I just want to take a quick look at just one example from that list. So this is the socket function. Really, the only thing we care about here is address family at the top and socket type, which is the second parameter. Address family is just where we're going to tell it, we're actually going to use, we're going to provide it with a 2, which just stands for AF-INET, which is address family internet or IPv4. And then the type is going to be 1, which is sock stream, which if you look up the definition for sock stream, it's a connection base with error handling, it's TCP. So we're going to use, we're going to set up our stager to use IP version 4 and a TCP socket. The rest are going to set to 0, which is actually kind of cool for us, because this is what I want to highlight in this case. If you'll notice at the top, we do the same trick. We're going to XOR the EDI register against itself to set that to null. And then we can just push EDI 4 times to get 0 for those last 4 parameters. And then what's neat, because it just so happens that we're pushing things in reverse, and we want 2, 1, 0, 0, 0, 0, we can push, 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 and then we can just increment EDI by 1, setting it to 1, push it, increment it again, and push it again. So just by managing that register and making efficient use of it, we're able to, with very minimal commands, get all of those parameters pushed for the socket function without having to reset values and change things around. We just used 1 register and just 2 increment commands, and we had everything we needed. And then just to point out again, like I was talking about earlier, EAX receives return codes from functions. In this case, EAX is what receives the socket descriptor. So we would then, of course, at the end would want to move the socket descriptor into another register to preserve it, because that's what we need to give to connect and receive to tell it use this socket for this function. So we want to save that. So let's see that in action. So I'm actually going to come over here. Oops. Whoa. There we go. So let's take a look at, we have stager.asm over here. This is the full shellcode. And I didn't want to go through all of this to bore you guys to death walking through all this shellcode, but if you are curious about it, this is what is, the construction of this is fully written up on my website in a blog post if you're curious about what each of these pieces is doing. That's all of the shellcode. So to get that to run, once you have shellcode you want to run, you just use NASM. Say, I'm actually going to see into whatever. Fine. Be that way. All right, so we're going to do stager. You just do NASM, you say, and then output it as stager.bin. There we go, it compiled. And then I have a Python script that I just use to quickly format this stuff. So there we go. We have an 86-byte stager, and there's our shellcode ready for a Python script. I already have it in the Python script, but one key thing we're going to need now is our listener. We need something for the stager to connect back to. And one thing to remember is that the listener can't be sending it this. The stager is going to be expecting that buffer, that receive buffer on the Windows side is going to be expecting like raw bytes. So I'm going to go ahead and use the message box shellcode we just took a look at. It's like there it is in shellcode form. And I've already gone through the trouble of, no, it was not that much trouble, but gone through the trouble of compiling with NASM. And so we can actually just set up a netcat listener on port 4444 and just pipe the message.bin into it. And we have our listener set up. And this is doing the exact same thing as like a Metasploit listener. You set up a listener from interpreter. This is all it's really doing. It's listening on a port, and it's being prepared to send that shellcode back. So over here, all we have to do is put that back. Our stager shellcode, set to shellcode, and we'll run it. So we have our debug pause, and we go, hey. And so we come back over here, we can see that indeed from the stager, the XP machine has connected back to our Debian machine, and the connection is actually still live. And so it'll stay alive as long as the process that's running the shellcode and running that connect and receive is still alive. And that will stay alive until we close this message box. So this is very similar if you've ever been messing around with an exploit, or you've been on a pen test or something, and you've gotten a command shell and you accidentally closed it or did something that broke the shell, and then it all died and you had to do the whole thing over again. This is why, because if or say you're in a process and the user closed the process or something, or it died and you lost your connection, this is why, because the shellcode is running in this message box process now. So once we close it, it's dead, and our listener is closed, which is then why, from like a pen tester side, like an attacker side, if you were doing this like through Metasploit, you start using like the interpreter's ability to migrate between processes to then initiate that connection through another process that will stay alive longer for you, rather than relying on the initial process. So I have a couple of papers and tutorials and things that I can point you to. The number one would be Scape's Understanding Windows Shellcode white paper. But there's other, that can be a little bit dense, especially if you're just getting started. So I would definitely recommend fuzzysecurity.com. Their tutorials are really fantastic. They have a whole bunch of different ones, from like game hacking to other ones that are usually written very well and have a lot of great information. They have really great stuff on even things like Windows privilege escalation and stuff like that. But their exploit development section is particularly good. Part 6 is dedicated to writing Win32 shellcode and actually gets into a little bit more of like what I did here with the message box and MSFN versus manual shellcode. They do message box as well as I think it's a WinExec to execute a command and do some compare and contrast there. So check that out. As well as Corlan. Corlan's website, they have a whole exploit writing series. There's also, I think it's part 9, has a full section on how to write Win32 shellcode. Those are much more dense and wordier. He tends to get into a whole lot of like details and get sidetracked and has a bunch of code examples. It can be a little bit hard to get through, but there's often some very good information in there that fuzzy security doesn't necessarily cover. And anyone have any questions or comments? Otherwise, that's all I've got.
Would you, do you have any resources to learn to, assembly and ASM?
Intel manual.
What's that?
The
Intel manual.
I mean, it's
Yeah.
that I have. Yeah, I didn't include them because I do have like a whole bookmark folder full of like little like reference sheets and stuff like that. Because especially with you go down that rabbit hole and you can find whole Stack Exchange threads with very heated debate over, for example, should you move 0 into a register or XOR it, or should you, which is more efficient? And then people citing like, well, this Intel employee told me it's meant to be this way, so it's the Intel. It gets weird. But yeah, other than like the Intel reference manual, there are a few websites and stuff out there that I can send you if you're interested that have some good reference material for certain types of commands. But beyond that, like actually getting into the reference material is probably the best way. Or one thing that does get a bit into assembly, and I learned a lot from, was the book Hacking the Art of Exploitation. Gets into a lot of that, as well as like C, and then it starts covering a lot of assembly, at least on a basic level.
So why assembly or assembler instead of like C?
For
when
shellcode?
you go to compile it, it all creates like code in the end. Right?
True. As far as like why, like, would you just write C for your shellcode? I mean, you're right. I do think it could be possible. I learned it this way. So honestly, there could be a reason that I just don't know of a limitation of what C allows you to do. Maybe you definitely would probably have finer control over the registers and things like that, going just straight to assembly. But I really don't know. Weirdly, I've become more uncomfortable in assembly than I am in C at this point. So, anyone else?
Why Nano
Yes.
instead of Vim?
Yeah.
I don't think I have Vim installed on that VM right now. I think that's why.
Supposed to use VI. It's everywhere.
I use the Vim though.
I asked the internet and they.
Yes, the internet. Hi, internet.
There's 8 streamers out there watching you,
Ooh,
waiting.
waiting,
You know one, unfortunately.
waiting for someone ask a question.
Yeah, I mean,
Or-
they're
or
behind
to
on
shut
the
it down.
stream, like X amount of minutes, so.
All right,
Martin says hi.
hi Martin. We're not going to talk about any 64-bit Martin. That's it. I know he did. He messaged me about it too.
That's it. Wait,
All right.
hold on. Wait. Do you use MS Vencode or MSF Venom to D0 assembly in his usual workflow?
Oh, do I normally use MSF Venom in my workflow?
And
Like-
MSF encode.
Or yeah, MSF.
MSF Venom, yes. Like I said, it's definitely more convenient to generate it that way. It's definitely more flexible. So yeah, like if I need shellcode, I will use MSF Venom. MSF encode, weirdly, I do not use that if I can avoid it. I will say, as an aside, that if you're doing any of the OffSec training, there are certain times that MSF encode does things differently and can actually create a payload that will work where MSF Venom does not. So it's something useful to keep in your back pocket if you're running into weird bad character issues or stuff like that. But typically I would use MSF Venom because MSF payload and MSF encode have been deprecated for like a year now, if not more. But you could also definitely use like MSF encode with your own manually written shellcode. Would be one benefit as well, because you can just give that a bin file, I believe.
Martin's real question is there a good reference for static offset of functions by different versions of Windows?
You know, that would be really handy. I just use a debugger. I load up that version of Windows and I use like Ali debugger and just search for it and find it. One thing I don't know for sure is if the addresses change or if they change very much depending on like language versions, because they could.
Yeah.
So I don't know if like English Windows XP Service Pack 3 has the same as like Windows XP SP3 NX or whatever it is, where it's like multi-language, or is it the same as Russian? Is it the same as the Korean Windows XP? They could probably all be different. So you'd have a massive reference.
That's it. That's all the questions.
All right.